All right, hello everybody. I'm Varun, and I'm joined by Mrunmayi over here to talk about streaming boot. Bharat's our muscle in the back. He's either working out or coding up the next demo, it's unclear. We're here to give an update on a continuing theme we've had of building streaming boot in the data center. So this is a slide we've presented for a couple of years now here at the OCP Security Working Group. And each year we've been trying to evolve the functionality that it has. The last time we presented this was a year ago on this stage, and it was called the Composable Security Architecture Episode 2. And the big changes from the previous one are using Caliptra as a root of trust for measurement, embedded in all of the devices that you see on the bottom. And then instead of having an external root of trust implementing update and recovery, we could have a streaming boot endpoint. The episode 1 that you saw before connects very well to, say, the OpenTitan presentation we had earlier about that discretized root of trust. Here we're trying to see what is the hypothetical, can we go beyond that? And that's the focus of our talk. So first, let's reiterate the problem statement. Why do we want to stream firmware at all? And the first is that flash is a total cost of ownership problem. Anytime a firmware update fails, it can lead to downtime. Firmware updates themselves take time because you have to write to these non-volatile media. And you could try to avoid that time by building background firmware update, but that is actually pretty hard to build. Like Jeff said, SPI is not a bus that likes to be interposed. It turns out it doesn't like it if you try to read it and write to it at the same time. So you need to do a lot of plumbing in order to make background firmware update work. The other piece is that flash is a security problem. Because it's non-volatile in a multi-tenant cloud, we want to be able to change the device ownership and usage from one tenant to the next. But that SPI flash is always something that could be carrying data from the previous tenant along the way. And that could be a virus or a bootkit, or it could just be some kind of bug that causes a denial of service. So the simple answer would be, let's just not use flash. But the answer to actually doing that might be a bit more complicated. And so to hand off how we're approaching this problem, I'll pass it over to Mrunmayi.
Thanks, Varun. So let's dive into some of the implementation details and our approach for streaming boot. Streaming boot itself can be thought of in two different stages. The first stage being early firmware download, and the second stage, the main firmware download. The advantage to this two-stage approach is to reduce device and implementation complexity, as well as to address PCIe, boot timing, and performance constraints. We propose leveraging the OCP recovery method for enabling that first stage, which is the early firmware download. The spec currently supports implementations over SMBus and I3C for this. You have to think of the early firmware as the minimal required firmware to adhere to PCIe requirements and also contain the root of trust for update that is needed for that second stage of firmware download. The second stage can then be implemented over a more performant protocol, specifically MCTP over I3C or USB, to fetch the rest of the firmware payload. So let's walk through an example of how the OCP recovery flow works as it stands today on an Nvidia Blackwell GPU. Before I get into the flow, let me introduce the pieces that are involved. MC here refers to a platform-level management controller that is the platform root of trust, which is the blue box that you see here. And then the second piece that's involved is our GPU. So first things first, the MC will reset the GPU into recovery mode. During this stage, no mutable firmware is loaded on the GPU. The recovery FSM, which is implemented in hardware, will change the GPU state from operational to recovery mode and get ready to receive recovery firmware over SMBus. The MC will then push the root of trust firmware as well as the management firmware over SMBus. The root of trust immutable ROM will authenticate this root of trust firmware and kickstart the execution. In turn, the root of trust firmware can then authenticate the management firmware and kickstart the execution of that. Both of these combined now support services that are required for the second stage, which is the main firmware download over PLDM type 5, over MCTP, over I3C. It's quite a mouthful. Then the MC can initiate a PLDM Type 5 firmware update with an operational firmware image. Once the update is complete, the MC can reset the GPU back into operational mode. So as you can see, two of the key pieces that are required to enable streaming boot on devices are already implemented. The first piece being OCP Recovery, and the second piece, PLDM Type 5. PLDM Type 5 has a lot of built-in flexibility to support streaming boot. It allows the firmware device to control the exact offsets and activation methods required for each component that gets transferred. This allows us to decouple the flash layout from the boot sequence itself. But there are still a couple blockers that we need to address. Since both SMBus and I3C are slower than SPI reads, PCIe timing requirements become a critical constraint. Also, any SBIOS resets that are issued at boot up or OS resets during runtime also become an issue, since they're out of view of the out-of-band platform root of trust. We want to solve these problems for PCIe devices. So we're working on power-on reset architecture and industry specs so that we can coordinate PCIe link-up with platform boot. Let's talk about some of the numbers that are involved here. Currently, the GPU recovery sequence on Blackwell takes 130 seconds. This includes the first 90 seconds for recovery firmware to be loaded over SMBus, and then 40 seconds for the entire new firmware image to be loaded over I3C. This is without any optimizations. We expect the value to only go down. The speed of flight, our theoretical best case for I3C, is 4 seconds. And the speed of flight for USB is 0.1 seconds, even lower. In comparison, loading the firmware image from SPI Flash takes 0.3 seconds. All that being said, let's put these numbers into perspective. A server today still takes multiple minutes to boot up due to DDR5 training. And a bad firmware update, either due to flash corruption or a bad image, could cause 2+ minutes of downtime for a server. Versus, with streaming boot, you just reboot that node with the old working firmware image. I'll pass it back to Varun to talk about the changes in the OCP recovery protocol next.
Thanks, Mrunmayi. What I like about this project is that we've been moving between execution on real silicon, like a Blackwell GPU, while also continuing to architect faster ways forward to make this an iterative program. So what we've been doing on the OCP recovery side is trying to increase the performance and the usability for streaming. First is we added a mode bit so that you could disable things like PCI watchdog timeouts to coordinate with the platform. The next functional piece we added is a feature called multi-stage activation, and that lets us load multiple images over the recovery interface. So if you have more dependencies in terms of firmware images to load your MCTP and PLDM stack, the spec now enables you to do that. The other two bullets that we added of late are to improve the performance. One is a FIFO-based configuration memory space. In the existing spec, it's random access, but it expects you to do one transaction at a time to load the data. Now we have a FIFO base that can do multiple outstanding transactions with a producer-consumer flow. So you don't have to be bottlenecked on the bus every single time. You can actually pipeline the data. And then the last piece is enabling support for I3C. And that alone is a 30x theoretical speed up over SMBus. And all of this is coming to life in the Caliptra subsystem as well. So we've heard about Caliptra subsystem in some of the earlier talks today. One of the specific pieces that's getting connected with streaming boot is an I3C implementation that implements the OCP recovery protocol and the MCTP over I3C protocol. And so the Caliptra root of trust handles the measurement and the authentication, and then the Caliptra manufacturer control unit, the MCU, handles the management firmware that can implement the PLDM and MCTP stacks. And there's a demo at the Microsoft Expo booth where you can see all of this running live, where the I3C recovery interface is being used to boot the Caliptra root of trust. And this is the overall Caliptra subsystem architecture where those pieces connect together. The Caliptra core is on the top. This is handling the authentication, the measurement. And then the MCU and the I3C controllers are at the bottom. This is the interface to the rest of the platform. And so that's how we have this two-pronged approach to executing functional parameters for booting the system while also doing it securely and reliably. All right, next steps. We have a lot of different specs and pieces to stitch together to make this proposal work, but it's showing signs of life in multiple areas, both in terms of Nvidia silicon efforts, Nvidia platform efforts, as well as Caliptra industry efforts. First is the OCP spec for recovery. This is publicly available today on the OCP website. It's in an RC point, and you're welcome to put comments on there as we march towards releasing it. Other things we want to do is add specific bits for streaming boot into the PLDM Type 5 packaging format, so it's easier to distinguish what you want to do with a given component. And then we want to connect all of these dots to the BMC and the platform root of trust architecture. One of the comments we've gotten is, how do I connect a PLDM package to an OCP recovery boot process? So we want to be able to document that for you. And we have a white paper that summarizes everything that we've talked about in this presentation. This is also publicly available too. And Caliptra Subsystem is the open source full stack implementation for all of these pieces. And you've heard timelines for that in one of the earlier presentations today. All right, the call to action, implement everything we talked about, or at least if you don't like it, tell us so we can learn something about it. All right, that's the end of our talk. Thank you.
Thanks.
Varun, you had a timing slide. How fast can we theoretically get it with the I3C? And is there benefits on looking at adding additional interfaces?
Yes. Did I lose it? Yeah, the timing numbers that we had were for 12.5 megahertz SDR, it'll be 4 seconds for speed of light. And for USB 2 at 480 megabit, it's 0.1 seconds. So there is a big benefit of USB. I imagine that USB will fan out, and so you won't see that 0.1 perhaps in aggregate to every device, but it's, there's a long way to go, and USB offers ample headroom. I3C too, I think, is a significant perf improvement over SM Bus and makes these features possible. They wouldn't have been possible with SM Bus before.
All right.
Hi, Varun. Thank you. I appreciate that for the effort over the years on this. So, sad to ask that how much SRAM is required now as a substitute to Spinor, since I believe that you will be chunking over the parts of the firmware, the management firmware down, and then do we have a correlation that if we increase the SRAM size, so how much bandwidth and how much timing it saves, and how about the case if at execution time the SRAM endures certain viral errors, ECC errors in the SRAM, then do we enter recovery again?
Great question. I think those questions are really dependent on your SoC or device architecture today. So if we take Caliptra as a nominal example, Caliptra only executes entirely out of SRAM today. And what it does to mitigate data corruption issues is it implements ECC logic on the SRAM. But because it's executing entirely out of the SRAM, streaming boot versus flash boot doesn't make any difference. It's just a matter of loading that SRAM with bytes. You have the SPI interface or these interfaces we presented today to do that. But once that loading is done, it's never going to touch that I/O interface again.
All right. Thank you. I appreciate the work. So currently, the SPI flash is used for storing data as well. So if you're eliminating the SPI flash entirely, is there a way to handle the writes or any initiation from the OCP to handle those things?
Yeah, that's a great question. Storing, per device unique data, for example, like field replaceable unit data or manufacturing diagnostic data, so on, that hasn't been a goal for us because our primary objective has been to get Flash out of the executable path. And I think to solve the data collection path, where you need data for field recovery, diagnostics, RMA, et cetera, I think that's going to end up being a problem that may be specific to the different kind of product that you have. Like a naive answer to that question could be, well, I could just push that data over MCTP to the BMC. But if the BMC is not your field replaceable unit, then how does that help with an RMA? But for certain markets, that might be okay. So short answer is it hasn't been our focus, but there's definitely opportunities there and stuff to work on in that area.
All right, thank you.
Thanks for the talk. I have a quick question. This streaming boot's scope is for the end device, and BMC is initiator for the whole streaming boot process. So is that possible to eliminate the SPI flash for the primary BMC boot?
That is a good question. I think it very much depends on the system architecture as a whole and what your top of tree is in terms of recovering a device. Like maybe someday you could even build a BMC that builds a network stack in ROM and then pulls it off of a management network somewhere, but you might not want to do that just because of how complex that could be and risky that could be. So there is, our goal right now is to solve the in the node problem where the BMC is the top of tree. And perhaps there'll be future engagements to say, how could we solve it for the BMC itself?
So that means currently we can still use the SPI as the local media to store to put the primary BMC.
Yeah.
Thank you.
Sorry, can BMC act as a root of trust itself?
I think that very much depends on your system security and product requirements. I think over the talks today, you've seen a variety of different ways that root of trust could be implemented. In the OpenTitan talk, you saw how an OpenTitan device could act as the platform root of trust and be the root of trust for the BMC itself. We've also seen talks with Caliptra and how it can be integrated into BMCs and serve as a root of trust. So there are multiple different modalities there.
Okay, then the answer is yes.
The answer is maybe.
Okay, thanks.
Does that SPI data rate make sense? You're saying that it's faster than I3C? And so why would anybody use I3C then?
The SPI rate is with talking to a SPI flash where you have fixed transaction latencies, you can't tolerate any drops. And so this example of a 90 megahertz dual SPI is with a SPI flash that's a few millimeters away from the ASIC and used to boot. But if I said, let's make SPI a streaming boot protocol, you'd have to wire that SPI line out to the platform root of trust. Your clock rates are going to go down dramatically as the trace length increases. You have to deal with the latencies of the SPI bus because when the device does that fast read, it's expecting the bytes for that firmware to come back within a fixed number of cycles. And so you're not going to hit 90 megahertz dual SPI when you do SPI as a streaming boot protocol. What we wanted to do is avoid those problems entirely by leveraging fabrics that already exist across the whole platform, namely the out-of-band manageability fabric. The reference platform today would not have SPI from every device going out to some platform root of trust. And instead, let's leverage a fabric that already exists. That other nice part about I3C and MCTP is that these are fabrics that tolerate loss. And so it can make these protocols a bit more resilient as they scale to larger and larger platforms.
Yeah. So I'm more familiar with SPI running at a much slower speed than 90 megahertz. That seems pretty fast for SPI.
Yeah, sometimes I regret doing that, but it works.
So just one quick question. So we went from local storage going slowly to now streaming it from somewhere. So now is there latency to get the image? That adds to the whole equation about how long the system takes. And if you have a fallback, for example, recovery, now you have to go and fetch the fallback firmware too. Does that latency matter? Do you prefetch them both and then toss one away?
Yeah, I think that's going to be a very interesting orchestration problem. because I think in this first example, what we've been showing in all these diagrams is a BMC or an AMC having all of the firmware images for all the devices in the platform. And depending on the rate of change, that could be something that gets done once a week, once a quarter. It could be stored in the eMMC connected to the BMC, so that time
So you're
gets
still
amortized.
thinking that the images for the streaming boot are still stored locally somewhere, just BMC's control?
I think
as
that'll
opposed to actually coming from
Yeah.
cloud storage.
Yeah, I think that would definitely be the first step. And then the next step would be evaluating, okay, this BMC has network access. Maybe I pull it from a cloud storage every time we boot. Are there advantages to that in terms of operational hazards that get avoided, but adds cost, like you said? We'll have to see.
Thanks.
All right. Thank you very much.